Okay, in today's lecture, we're going to finish up the section 5.3 material on double integrals using polar coordinates. And in the last part of this section, we're going to talk about how we can use double integrals to find the area enclosed by some polar curve, or the area of a region maybe between two polar curves. So we have the following theorem, which tells us how to find area using polar coordinates. And it says that the area of some polar region D, which would be bounded by the graph of some polar curve R is a function of theta, for values of theta between alpha and beta, is given by evaluating the double integral of 1 over the region D. So recall that one of the properties of double integrals is that they can be used to find the area of some region D if we integrate the function 1 over that region. So here, if we make use of polar coordinates, we can express that double integral as an iterated integral, where our outer integral with respect to theta ranges from alpha to beta, and our inner integral with respect to r ranges from 0, that is from the origin, out to the value of r, defined by this function f of theta. And the differential of area in terms of polar coordinates, remember we pick up that extra factor of r, so we have 1 r dr d theta. So evaluating the antiderivative of this first with respect to theta, or with respect to r, we would have 1/2 r squared from 0 to f of theta. So that leaves us with the constant 1/2, which we can pull out in front of the integral. And then r squared, evaluating at f of theta, gives us f of theta squared. And so then we integrate this function with respect to theta. So this formula for the area of a region bounded by a polar curve, we've actually already seen when we were looking at the section 1.4 material. So we can use a double integral to define the area of this polar curve, and after we evaluate that inner integral, we're left with a single integral of 1/2 of the function squared with respect to theta over the theta interval. So we haven't done some problems like this in a while, so let's look back at some examples. So in this first one, we are asked to find the area of the region enclosed by the cardioid. R is equal to 1 minus sine of theta. So let's start by sketching our region here. So here in the xy plane, we're talking about a region enclosed by the cardioid 1 minus sine of theta. So when theta is 0, we have 1. When theta is pi over 2, we have sine of pi over 2 is 1, so r would be 0. When theta is equal to pi, we have 1 minus sine of pi, which leaves us 1. So we're moving outward 1 unit from the origin along the negative x-axis. And then when theta is equal to 3 pi over 2, sine of 3 pi over 2 is negative 1. So we have 1 minus a negative 1, which gives us 2. So here our cardioid looks something like this, and we want to find the area of the region enclosed by that cardioid. So here, using our new theorem, which really is the theorem we've already looked at from earlier in the course, just expressed in terms of a double integral now, we can find the area of this region by looking at 1/2 the integral of our function for r, which in this case is 1 minus sine of theta squared, integrating with respect to theta. And our interval for theta here would be from 0 to 2 pi. So we see that this region occupies all 4 quadrants of the xy plane. So to get the full region, we would have to integrate from 0 to 2 pi. So to evaluate this integral, we would start by expanding. So we have a 1/2 integral from 0 to 2 pi of 1 minus 2 sine theta plus sine squared theta d theta. So the first 2 terms are pretty easy to integrate. This last term, sine squared of theta, to integrate this, we would make use of a trig identity similar to what we saw for cosine squared of theta. So here we could rewrite that last term of sine squared theta as 1 minus cosine of 2 theta all over 2. And we're then integrating with respect to theta. So let's see what we have here. If we combine some like terms, we have a 1/2 integral from 0 to 2 pi of, so let's look at which terms we can combine in our integrand. Here we had a constant of 1, and then I'm adding a 1/2. So that leaves me with 3/2 minus my 2 sine theta. And then on the end, we had a minus cosine of 2 theta over 2. So we can write that as minus 1/2 cosine of 2 theta. And we're integrating with respect to theta. So here, let's find our antiderivative. We have our constant 1/2 times 3/2 theta plus 2 cosine theta. And for our last term, we have a minus 1/4 sine of 2 theta, where we're evaluating from 0 to 2 pi. So we have a 1/2 times, when we evaluate this antiderivative at 2 pi, we have 3 pi plus 2 times cosine of 2 pi. So that leaves us with 2. And then minus 1/4 sine of 4 pi, which is 0. And then we're subtracting what we get when we substitute 0 in for theta. So our first term, we have 3/2 times 0 plus 2 times cosine of 0, which gives us 2, and then minus 1/4 sine of 0, which is 0. So here our plus minus 2 terms cancel, and we're left with 3 pi over 2 for the area that lies inside of that cardioid shown above. So a little refresher on how to find the area bounded by some polar curve. So let's look at an example of finding the area of a region bounded by 2 polar curves. So in our next example, we're asking for the area of the region that lies inside of the circle. R is 4 sine of theta, and outside the circle of constant radius, r equals 2. So here, in order to sketch our region, or try to visualize the region we're talking about, we need to find where these 2 curves intersect. And this will also allow us to determine what the range of our theta values will be for our integral to find this area. So let's start by setting these 2 curves equal to each other. We're going to let 4 sine of theta equal 2, which means that sine of theta is 1/2. And so solving for theta, we have theta could be pi over 6 or 5 pi over 6. So let's see if we can visualize our region here. So we're looking at a plane region in the xy plane, where one of our curves is the circle of constant radius 2. So we have a circle centered at the origin, constant radius. And then we had the circle r equals 4 sine of theta. So here when theta is 0, r is 0, so it's going to pass through the origin. When theta is equal to pi over 2, that is along the positive y-axis, r is given by 4. So we end up with a circle that's lying in this upper half plane. And we see that these two circles are intersecting when the value of theta is pi over 6 radians, or when theta is given by 5 pi over 6. So we want the area of the region that lies inside of that circle defined by 4 sine of theta, but outside the circle of radius 2. So we're talking about the shaded region shown here. So to find our area for this region, we're going to take the area that lies inside of that first circle, which we would find by evaluating 1/2 the integral from pi over 6 to 5 pi over 6, the outer function, or the outer curve, which was given by 4 sine of theta squared, and then we subtract the area that lies inside of the circle of radius 2, which we would find by taking half the integral over the same interval of our inner curve, or inner circle, which was r equals 2 squared, and then we integrate with respect to theta. So if we simplify a little bit here, there's a few ways that we could approach this in order to make our work a little easier. So one thing that I'm going to make use of here is the symmetry of this region. I see that if I were to find the area of the part of this region on the theta interval from theta equals pi over 6 up until theta equals pi over 2, that is along this positive y-axis. If I find that area shaded in red, I could double it to get the area of this full region. So here, making use of symmetry, of this region, the area could be found by taking twice the area of this region from pi over 6 to pi over 2. And the reason that we might do this, it's a little easier to evaluate our trig functions at a value of pi over 2 instead of, say, 5 pi over 6. So here, if we expand our integrand, 4 sine of theta squared gives us 16 sine squared theta, minus 2 squared is 4, and we're integrating with respect to theta. So here our constants 2 and 1/2 will cancel, and we're left with the integral from pi over 6 to pi over 2 of 16 sine squared theta, minus 4. Now, to evaluate the antiderivative for a sine squared function, we're going to make use of that same trig identity, where we have sine squared of theta is 1 minus cosine of 2 theta all over 2, then subtracting 4 and integrating with respect to theta. So we have the integral from pi over 6 to pi over 2 of, well, let's combine some terms. If we distribute our 16 with this constant of 1/2, we have 8 minus 8 cosine of 2 theta minus 4 that we are integrating with respect to theta. So grouping our constants, we have the integral from pi over 6 to pi over 2 of 4 minus 8 cosine of 2 theta, d theta. So finally, we can find our antiderivative as 4 theta minus antiderivative of 8 cosine 2 theta gives us 4 sine of 2 theta. And we're then evaluating from pi over 6 to pi over 2. So substituting pi over 2 in for theta, we have a 2 pi minus 4 times sine of pi, which is 0. And then we're subtracting what we get when we plug in pi over 6. So we would have 4 pi over 6 or 2 pi over 3. And then minus the negative, we have a plus 4 times sine of 2 pi over 6. So that's the same as sine of pi over 3, which is square root of 3 over 2. So multiplying by the constant 4 out in front, we have 2 times the square root of 3. And combining our first two terms, 2 pi minus 2/3 pi gives us 4/3 pi plus twice the square root of 3. So this would be the area of the region that lies between those two circles described in terms of those polar functions. So in the last part of this section, let's look at a couple of examples of calculating area bounded by polar curves. Maybe we won't go through the full work of evaluating the integral, but in these last examples, we are asked to set up an integral for the area of some region between curves. So in this next one, we're looking for the area of the region that lies inside of the circle r equals 3 cosine of theta, in which lies outside the cardioid 1 plus cosine of theta. So as with our last example, we may want to try to visualize this region, or certainly we need to determine where these two curves intersect so that we know our region of integration for theta. So here, to find where these curves intersect, let's set these two functions equal to each other. We're going to let 3 cosine of theta equal 1 plus cosine of theta. So we find then that 2 cosine of theta is 1. So cosine of theta is then 1/2. So theta would then be given by plus or minus pi over 3. So here we can try to visualize our region. So we're looking at some plane region in the xy plane, which lies inside the circle 3 times cosine of theta. So when theta is equal to 0, we have a value of 3. When theta is pi over 2, we have 0. When theta is equal to pi, we would have 3 times cosine of pi, so -3. So from this negative x-axis, we would move -3 units outward. So we're moving back to this point 3, 0, moving in the direction of the positive x-axis. So here our circle looks like the following. This 3 cosine of theta. And then we're looking for a cardioid, 1 plus cosine of theta. So when theta is 0, we have 1 plus 1, or 2. When theta is equal to pi over 2, we have 1. When theta is equal to pi, we have 1 minus 1, or 0. And then when theta is equal to 3 pi over 2, we have r equals 1. So our cardioid looks something like this. And we see that the theta values that define the intersection of these curves are given by positive pi over 3 or negative pi over 3. So here, the region of interest is the region that lies inside of that circle, but outside of the cardioid. So our shaded region shown here. And again, to find this area, well, there's a couple of approaches we could use. The direct approach to find our area would be to integrate 1/2 of our outer curve, which was the circle, 3 cosine of theta squared, minus the inner curve, which was given by 1 minus cosine of theta quantity squared. So we would integrate with respect to theta over the interval where these curves intersected. So in this case, from negative pi over 3 to positive pi over 3. Or if we wanted to make use of symmetry, again, if we were to find the area of this region shaded in red, that is going from theta equals 0 to theta equals positive pi over 3, I could then just double that region to get the area of interest. So making use of symmetry, another way we could set up this integral would be as 2 times this 1/2, which would give us 1, times the integral from 0 to pi over 3 of our 3 cosine theta squared minus 1 plus cosine of theta quantity squared d theta. So here, either of these integrals would give us the desired area. And in this problem, we were told just to set up this integral, we don't need to evaluate it. If we had to evaluate this, we would need to expand everything and make use of the trig identity for cosine squared to get our antiderivative. So let's look at another one, sort of similar to this. In this last example, we are asked to again set up an integral for the volume of a solid which lies above a cone defined by z equals the square root of x squared plus y squared. So here let's sketch our solid region that as we're going through the problem. So we have the cone z is positive square root of x squared plus y squared. So that would be the upper half of the cone, that lies above the xy plane, where our cross sections are circles, and it lies below the sphere defined by the sum of x, y, and z squared is equal to 1. That is the unit sphere. So here, since we're looking, or since we're only interested in the part of this solid that lies above the cone, we only need to consider the top half of our sphere, or the upper unit hemisphere. So we have some upper half of our sphere that looks like this, and my cone is then intersecting this sphere, and it looks like a circle. So we want the volume of the solid that lies below that sphere, or below the upper hemisphere shown in blue, and above this cone. So in order to evaluate the volume of a solid or that's bounded by two surfaces, we could start by finding the volume of the solid that lies underneath this larger surface and above some region in the plane. And then we would subtract the volume of the solid that lies below our cone to get the volume of the solid between these. So here we need to know what region in the xy plane we're integrating over. And to find that, we need to know where do these two surfaces intersect. We see it looks like they intersect in a circle, but what is the equation for this circle? Because if we project that circle down onto the xy plane, we see that this disk is going to be our region of integration for this double integral. So in order to find the curve of intersection for these two surfaces, let's see if we can set them equal to each other. So here we had the equation of the sphere, x squared plus y squared plus z squared is equal to 1. And the equation of our cone was z equals the square root of x squared plus y squared. Or if I square both sides, z squared is equal to x squared plus y squared. So if I take the equation for this cone and I substitute it into the equation for the sphere, I have 2 times x squared plus y squared is equal to 1. So x squared plus y squared is then 1/2. So this curve of intersection for these two surfaces is given by x squared plus y squared equals 1/2. So circle centered at the origin of radius 1 over the square root of 2. So our region of integration, D, shown in the xy plane, is going to be the disk where x squared plus y squared is less than or equal to 1/2. As we want all the points on that circle, which is the edge of our boundary, or the edge of our region D, and then every point that lies inside that region. So now let's see if we can set up our expression for the volume. It's going to be the double integral over D of the larger surface. So here we were talking about our upper surface being the hemisphere, where x squared plus y squared plus z squared equals 1. Now, if I'm thinking about that upper hemisphere as the graph of a function, I would need to solve for z. So if I solve for z, I would have the square root of 1 minus x squared minus y squared for that upper hemisphere. I take the positive square root since I'm talking about the top half of my sphere. So we would have the following. And then we would subtract the volume of the solid that lies underneath our cone, which would be found by taking the double integral over the same region D of the equation for our cone, which was z equals the square root of x squared plus y squared. Integrating with respect to A. So here we see from our work that this region D is a disk. It's most easily described using an iterated integral, making use of polar coordinates. So using polar coordinates, that disk would be described as a range of values for theta from 0 to 2 pi, since we're considering the full disk. And the outer radius would be the circle, or the outer edge of that disk would be the circle of radius 1 over the square root of 2. So our range of values for r is from 0 to 1 over root 2. So expressing our function in terms of polar coordinates, we have the square root of 1 minus x squared plus y squared is given by r squared. and then minus the square root of x squared plus y squared, which would be the square root of r squared. So we're left with just r. And then the differential of area in terms of polar coordinates is r dr d theta. So here we have the integral from 0 to 2 pi, and from 0 to 1 over the square root of 2. If we distribute our r, we have r times the square root of 1 minus r squared minus r squared dr d theta. So this would be an integral for the volume that we're interested in. And here we were told we just have to set it up. We don't need to evaluate it. If we needed to find this volume, we could find our antiderivative by making use of a substitution from here.